When a 240 volts, 20 amp street lighting branch circuit requires number 8 American wire gauge because of voltage drop, the grounding conductor does not automatically have to be number 8 American wire gauge as well. The sizing of the equipment grounding conductor is determined by the size of the overcurrent protection device protecting the circuit, and not by voltage drop considerations. To properly size the equipment grounding conductor, you need to refer to the relevant electrical codes, such as the National Electrical Code, specifically Table 250.122. This table provides the minimum size requirements for equipment grounding conductors based on the rating of the overcurrent protective device in the circuit. The overcurrent protective device, such as a circuit breaker or fuse, is what determines the maximum current that the circuit is designed to carry safely. Voltage drop occurs when the voltage at the end of a long circuit run is less than the voltage at the source. Increasing the conductor size reduces voltage drop, but it does not change the amount of fault current that could flow in the event of a ground fault. The equipment grounding conductor's purpose is to provide a low impedance path for fault current back to the source, allowing the overcurrent protective device to trip quickly and clear the fault. The size of the equipment grounding conductor needs to be adequate to handle the maximum fault current that could flow, and the overcurrent protective device rating dictates this current level. For a 20 amp circuit, Table 250.122 of the National Electrical Code typically requires a number 12 American wire gauge copper equipment grounding conductor. This is generally sufficient for a 20 amp circuit, regardless of the branch circuit conductor size. However, there are exceptions and special circumstances to consider. One such exception is found in Section 250.122b of the National Electrical Code. It addresses situations where grounded conductors are increased in size for voltage drop. In such cases, the equipment grounding conductor must be proportionately increased in size as well, based on the increase in size of the ungrounded conductors. For example, if the ungrounded conductors are increased from number 12 American wire gauge to number 8 American wire gauge to address voltage drop, and this represents a threefold increase in area, then the equipment grounding conductor must also be increased by the same proportion. If the original equipment grounding conductor was number 12 American wire gauge, you would need to increase its cross-sectional area to match. This may or may not require going to a number 8 American wire gauge. The calculation for this increase is based on circular mil area. You would determine the circular mil area of the original equipment grounding conductor, multiply it by the same factor used to increase the phase conductors, and then select the standard wire size that has a circular mil area equal to or greater than this new value. Another consideration is the type of wiring method used. Different wiring methods have different requirements for grounding. For example, if the street lighting circuit is run in rigid metal conduit, the conduit itself can serve as the equipment grounding conductor if properly installed and maintained. In this case, a separate equipment grounding conductor within the conduit may not be required. However, it is best practice to always include an equipment grounding conductor, especially in outdoor applications where corrosion and other factors can compromise the integrity of the conduit. When using metal conduit as the equipment grounding conductor, proper bonding is essential. All metal enclosures, boxes, and equipment must be properly bonded to the conduit to ensure a continuous low impedance path for fault current. Bonding dampers are used to connect these components to the conduit, and they must be sized according to the same requirements as equipment grounding conductors. It is also important to consider the length of the circuit run. In long circuit runs, the impedance of the equipment grounding conductor can become significant, which can reduce its effectiveness in clearing ground faults. In these cases, it may be necessary to increase the size of the equipment grounding conductor to reduce its impedance and improve its performance. When determining the size of the equipment grounding conductor, it is always a good idea to consult with a qualified electrical engineer or inspector. They can help you assess the specific conditions of the installation and ensure that the grounding system meets all applicable code requirements. In summary, while the size of the ungrounded conductors in a street lighting circuit may need to be increased to address voltage drop, the equipment grounding conductor size is primarily determined by the rating of the overcurrent protective device and the requirements of the electrical code. Section 250.122b of the National Electrical Code addresses situations where the ungrounded conductors are increased for voltage drop, and it provides guidelines for proportionally increasing the size of the equipment grounding conductor as well. Always consult the applicable electrical codes and a qualified professional to ensure that the grounding system is properly designed and installed. Remember that a properly sized and installed equipment grounding conductor is critical for electrical safety, and it helps to protect people and equipment from the hazards of electrical shock and fire. The primary function of the equipment grounding conductor is to provide a low impedance path for fault current to return to the source. This low impedance path ensures that the overcurrent protective device will trip quickly, interrupting the flow of fault current and preventing damage or injury. If the equipment grounding conductor is too small, it may not be able to handle the fault current adequately, which could delay the tripping of the overcurrent protective device and increase the risk of electrical shock or fire. Therefore, it is essential to carefully consider the size of the equipment grounding conductor and ensure that it meets all applicable code requirements. In addition to the size of the equipment grounding conductor, it is also important to consider its material. Copper and aluminum are the two most common materials used for equipment grounding conductors. Copper is a better conductor than aluminum, but it is also more expensive. Aluminum is lighter and less expensive than copper, but it has a higher resistance. When using aluminum equipment grounding conductors, it is important to use appropriately sized conductors and to ensure that all connections are properly made to prevent corrosion. Corrosion can increase the resistance of the connection, which can reduce the effectiveness of the equipment grounding conductor. It is also important to protect the equipment grounding conductor from physical damage. If the conductor is damaged, it may not be able to handle the fault current adequately, which could increase the risk of electrical shock or fire. Therefore, the equipment grounding conductor should be installed in a protected location, such as inside a conduit or raceway. Regularly inspect the equipment grounding conductor to ensure that it is in good condition and that all connections are tight and free from corrosion. If any problems are found, they should be corrected immediately. A properly maintained grounding system is essential for electrical safety, and it helps to protect people and equipment from the hazards of electrical shock and fire. Finally, always remember that electrical work can be dangerous, and it should only be performed by qualified professionals. If you are not comfortable working with electricity, hire a qualified electrician to do the job. An electrician has the knowledge, skills, and experience to safely and properly install and maintain electrical systems. They can also help you ensure that your electrical system meets all applicable code requirements. The overcurrent protection device is critical in the safety of the branch circuit. If there is a ground fault with the electrical system, the overcurrent protection device is there to trip the electrical circuit. The grounding conductor is sized based on the rating of the overcurrent protection device in order to have a low impedance path back to the source to allow the overcurrent protection device to operate as required. If the ungrounded conductors are increased in size due to voltage drop, the increase in size of the equipment grounding conductor is proportional to the increase in the size of the ungrounded conductors. The grounding conductor is required to be protected as well, so that it does not become damaged. This is to ensure that there is always a low impedance path in the event of a fault to send the fault current back to the source, allowing the overcurrent protection device to operate. Always use a qualified electrical professional if you are not experienced and comfortable working with electricity. They have the proper knowledge and experience to perform the electrical work safely.